All right, so my name is Brian. I'm a sixth-year grad student from the Department of Biophysics, and I got my bachelor's at University of Florida, and my advisors is Dr. Bashir in bioengineering, electrical engineering, and Sue Claire from Indiana University School of Medicine. And so today I'm going to talk about label-free electronic detection of cancerous biomarkers using silicon nanowire arrays. So just a brief outline of what I'm going to go through, just the introduction to the technology and the principles, the motivation of why to use these type of sensors and the clinically relevant targets, our results, and what we've been able to change and progress, and what we're currently working on. And so basically, the whole concept revolves around ISFETs, or ion selective field effect transistors. And so basically an ISFET is nothing more than a MOSFET with the gate insulating layer exposed. And so you can see here, basically MOSFETs are the fundamental pieces and building blocks for all of your computer chips and CMOS technologies. And so I just have an example of an Intel node MOSFET here. And the only difference between a commercial-based ISFET for sensing pH and this is that the gate layer is replaced by a reference electrode. And so basically for ion selective field effect transistors for biological sensing, the whole principle revolves around an analyte binding to the surface and a chemical or biological recognition element to sense that analyte. And so basically you can see the concept governing a MOSFET and an ISFET is essentially the same for when a device turns on, called the threshold voltage. And the only differences are highlighted in blue, where instead of having a top metal, you have a reference electrode which has a certain reference potential and dipole to it. And so the principle is when an active area is functionalized, target molecules that have a charge bind to it, and the binding of the molecules changes the threshold voltage with the concentration. And the net effect of the change in the threshold voltage we can detect electronically. And so currently right now, is integrated semiconductor biosensors are actually becoming quite prevalent. And one of the main demonstrations is recently in Nature was Ion Torrent. Some of you maybe have heard of them. They got recently purchased by Life Technologies for electronic genome sequencing. And so basically, in accordance to Moore's law, transistors per chip approximately double every 2 years. So this is a very up-and-coming technology that moves very rapidly. And so the great parts of it is that it's a CMOS compatible method that you can do in foundries, and it has a low cost of manufacturing and possibilities of millions of sensors. And you can just see on the right side here, this is taken from Ion Torrent's actual paper, and this is a cross-section of what their actual device looks like, which they are actually finding in a lot of hospitals now, and they're trying to market to compete with fluorescent-based methods for genome sequencing. And so the whole principle of silicon nanowires, which is the part that I work on. In recent years, with Intel's coming out with Tri-Gate technology, the 22 nanometer mode, and FinFETs, that's basically the main principle of a silicon nanowire, is that by having a small length to width ratio, you're able to electrostatically modulate the channel a lot better, which should give you better sensitivity. And so I just have as an example what a classic FinFET looks like, and the concept of a silicon nanowire basically revolving around what they call the hose effect. So you have a smaller radius and smaller widths. The binding molecules will actually affect the conduction of the channel more in the threshold voltage than if you had a larger system. And so basically that is the main principle revolving around silicon nanowires and why you want to use a small system versus a larger type of MOSFET or something that would be 10 years ago. Basically 180 nanometer, 350 nanometer node. And so this on the bottom here is just a reference talking about the schematic setup of how we measure devices and measure their functions based upon a silver chloride reference electrode and an electrolyte, which we have the analyte, and a source and a drain, which is connected through this circuit here. And we apply voltage to the fluid gate and measure the current to the drain. And so just talking about the motivation for these applications with silicon nanowires. And so you can see the applications people have used them for electronic detection, because most biological molecules contain charge. And so you're able to sense, as long as you have the proper recognition element on the surface, a lot of different types of molecules, including biological, proteins, DNA, RNA, but then also chemical, as she was talking about earlier, with heavy metal ions. If you have a proper chelator on the surface, you're able to sense that charge as well. And of course, pH, which the whole principle of ISFETs is based on. But a lot of other reactions generate hydroxyl groups and protons, which you can also measure directly on a surface, which is based on the whole ion torrent system and how they measure genome sequencing. And so gases as well. If you have a proper catalyst on the surface, you can sense detections of nitrous oxide, hydrogen, and other volatile organic compounds. And so our main purpose and what we've been working on is breast cancer biomarkers, and specifically microRNA. And so microRNAs are an abundant class of gene regulators, been shown to control a wide range of biological functions, such as cellular proliferation, differentiation, and apoptosis. And some of them map within fragile regions of chromosomes, which are areas that are associated with various human cancers as well. And they can also function as tumor suppressors and oncogenes. And so there's been a lot of research recently into determining the upregulation or downregulation of these targets. Some of the ones that we've been concentrating on are MIR10B, MIR21, and MIR125, which are associated with breast cancer and being upregulated or downregulated. And so to talk about our results and some of the challenges that we face and how we've overcome them, and the sensing of the microRNA targets and their limits of detection that we've been able to achieve. And so, like I was talking about earlier, ISFETs is basically a transistor that you put in fluid. But I'd like to talk about it in terms of the main challenges we face is, would you take your computer and use it in your swimming pool? That's a big problem because things short circuit and you have major issues with leakage. And that's one of the problems that most silicon nanowire based technologies face, is that basically you want to have a oxide or a gating dielectric which is able to resist leakages and provide a good subthreshold slope. A good subthreshold slope, which is this. The subthreshold regime is this here. So naturally, the better the slope, the better your detection limit is going to be, because smaller changes in the voltage will lead to larger changes in the current. And so some of the issues is that to remove gate leakage, you want to have a thick oxide or a thick gate dielectric, but the problem is that you get a lot of drift and a lot of charge. And so you can see here, the changes in the threshold voltage could be 220 millivolts, and the slope is pretty poor. Nowadays, with a modern transistor, you're very close to 70 millivolts per decade instead of 700 in today's technology node. And then, but when you want to get a better capacitive coupling, the issues that occur with a thin oxide, circa 5 to 8 nanometers, you have way too much leakage current, and that degrades the device performance, as you can see. And so the main issue of how we solve these problems was high K dielectrics, which is also what's found now in the lower technology nodes, 45 nanometers, Tri-Gate, and 32 nanometer technologies. And so by having a high K system as opposed to silicon dioxide, you're technically able to make a thicker dielectric layer while maintaining the same capacitance as a thin system. And so you're able to get the best of both worlds, essentially. And so basically what we had to do is we chose hafnium oxide. And hafnium oxide is a very good high K dielectric. It has a very large atomic radius and a small lattice constant. So what's great about it is that the diffusion of ions, such as sodium and the smaller ones and lithium, it's very small. And so what we were able to do is characterize the hafnium oxide that we deposit through atomic layer deposition and optimized it to be able to act not only as a good dielectric, but as a very good etch stop. So you're actually able to wet etch it without overcoming some of the problems of also etching your gate dielectric. And you can see that a lot of the nasty compounds which you'd find in semiconductor industry really rarely, after you anneal the system and optimize it, rarely affect the system. And you can see here through the thickness over time how when it's unannealed and unoptimized, it degrades, but it acts as a great etch stop when you do this. And so the other part is that not only you want it optimized chemically, but electrically. And so by doing these same procedures, we were actually able to remove a lot of that effective charge that caused that drift that you saw earlier, and remove a lot of the hysteresis, which is caused by interface traps or interface charge that gets filled. And so by doing this, we were able to make the parameters comparable to what you'd see in industry these days of about 20 to 22 for the dielectric constant of hafnia. And so this is our final base device. And so you can see it here, an optical micrograph on the left, which deals with the leads, the passivation layer, which protects the leads, and the release window with the nanowires inside. And an SEM image is on the right, which shows the overall release area, and the nanowires, which are about 100 to 150 nanometers. And you can see a cross-section image of it right here, where this is the nanowire in the center here. This small area around here is the gating dielectric. And this part on top of it is actually a metal sputtered to get the contrast. And so as comparison, we also have what we have called a microwire or a nanoplate. And so they're about 50 to 100 nanometer wide and 30 nanometers thick. And so they operate in accumulation mode. So the holes or positive charges are the carriers. And so these use a 15 nanometer thick HFO2 layer, which has an equivalent oxide thickness of about 3 nanometers, or corresponds to about a 180 nanometer node process. And we use a reference electrode, which is silver chloride. And like I was talking about earlier, we measure the drain current versus the electrode voltage. And it's plotted, and we are able to extract the threshold voltage based upon that and changes. And so by doing that, you can see how we've been able to improve the performance of a device in a fluid-based environment. Now we have a subthreshold slope of 100 to 112 millivolts per decade with a change of maybe 2.7 millivolts. And you can see how the fluid leakage is almost non-existent. And so the device performance has been improved greatly, and so by doing that, we're actually able to do the proper measurements for DNA sensing and sensing of small amounts of charge on the surface. And so the first thing to test the principle is doing pH measurements of the nanowire, because hafnium oxide, like any other silicon dioxide system, when you change the pH, you change the voltage on the surface, or the surface potential. And so we just took current voltage curves to see the stability and what the system's operating capabilities were. And so you can see that we changed from pHs 4.6 to pH 10.7 and back to 4.6. And what's important here is that when you change it back to the original pH, the curve overlaps exactly where it was in the beginning. And so just the brief thing about the pH sensitivity is that you can see that's about 56 millivolts per pH and 51 for the microwires or nanoplates. And basically, that's pretty close to what you'd find for an industry-based standard for a type of sensor, which is very good. And so the second part which we had to optimize was device functionalization. And so I'll talk about the brief parts that we did in using polyol lysine to cross-link the DNA to the surface. So it will eventually electrostatically bond to the hafnium oxide in the proper pH. So we use a pH solution of about 8. Hafnium oxide has an isoelectric point of 6, so it's negatively charged when the polyol lysine is positively charged. We electrostatically absorb it and cross-link it through baking to the surface, and then we put down the target DNA or RNA, which then can hybridize to the surface. And so the first thing we wanted to do is there's all types of polyol lysines. So we wanted to figure out what would give us the most uniform layer on the surface while giving us the best sensitivity. Because what you want to have is the charge that you want to measure needs to be as close to the surface as possible to get the best sensitivity. So you don't want a thick cross-linking layer, or else you're going to lose that sensitivity. So what we wanted to make sure was that we were able to get an actual monolayer of the polyol lysine. Yeah?
You have a question?
Uh-huh.
We can't see.
You can't see it? Okay. Now can you see it?
Yeah.
Yeah?
Thanks.
Okay.
Sure. Okay.
Thank you.
Okay. And so basically this is just talking about because there's different types of polyol lysine with different molecular weights out there. So we tried one of the more commercial-based ones, which is 70 to 150,000 molecular weight, and a smaller one, which is about 9 to 14,000. And so this is just an image on the left, just talking about the basic process, which was on the previous slide. And so what we did to characterize this is atomic force microscopy. And so we took an untreated hafnium oxide deposited surface and put polylysine on it and the two different types. And then applied a force to the AFM tip to scratch away the layer. And then did a tapping mode image afterwards to measure the thickness. And so you can see from the two morphologies that the thickness overall is about 1 nanometer, which indicates the true monolayer of the polylysine on the surface. But you can see the roughness of the polylysine on the right, the higher molecular weight one, is much rougher than the very smooth surface for the polylysine 9 to 14,000 molecular weight. And so we just talk about the probe deposition optimization. And so you can see from before that the probe put on the surface, the DNA probe put on the surface, is a higher density with the smaller molecular weight one as the larger one, which is also what kind of was indicated from the AFM measurements. So this was another experiment that we did actually on the nanowires. And you can also see that there's minimal binding to the bare surface, which is really good, which means that the procedure that we use to rinse the system and to link it is pretty reproducible and gives a high specificity. So this is just measuring this on the nanowires. And so you can see the buffer, the probe, and the polylysine. So when you put the polylysine down, it shifts one way. And then when you put the probe down, it shifts the opposite way because its charge is opposite, meaning that as a sanity check, we're making sure that all of these things go down properly and that we're sensing things in the proper charge manner. And so this is the microRNA sensing results using MIR10B as the target, and the mismatch was MIR21. And so these were done on nanowires with varying concentrations from 100 femtomolar all the way up to 1 micromolar. And so you can see that with those two different molecular weight polylysines, that with the smaller molecular weight one, we're actually able to detect down to 1 to 10 femtomolar theoretically, and at least to 100 femtomolar using the nanowire in our protocol. And so the simulation here is just a simulation match to our experimental data. And you can see that there's a very large dynamic range that at this point in time we're still able to detect from 100 femtomolar all the way up to 1 micromolar in a linear range.
What kind of simulation are you performing?
Oh, it's a numerical simulation
based
using,
on the theory?
Yeah, exactly, based on the theory. And so just to talk about the work in progress that we're doing right now with this results and these devices is that ideally we want to measure the microRNA in a multiplexed environment. And so what we're trying to develop now is to take cells and be able to lyse them on chip, which people are actually in our group are actually doing at this point in time, and be able to spot the individual probes for the different targets on an array and be able to sense them. And this is just a schematic. And so what was nice is that we were able to sense within the clinically relevant range of 10 femtomolar to 10 picomolar in, for these levels on our device, which makes it promising that we're able to detect these from these cell lysates. And so the part that we're also working on now is an integrated device. So being able to take one of our chips, which you see on the left here, you see on the left part here, and be able to put it into this package whereby you have this O-ring with these flexible pins, which then contact an integrated circuit device where we can actually have a multiplexer that measures multiple different devices at the same time with different probes. And you can see that it will actually hook in through these BNC cables here to monitor the output. And so that's currently what we're working on now. And so I want to thank you guys for your attention, and want to acknowledge my colleague Bobby, who also worked with this tirelessly, and the staff at MNTL for helping with a lot of the clean room equipment that we have to use to process these devices. So I'll take any questions you guys have.
Any questions from U of I and from UC Merced? I have a question for the pH sensors.
Mm-hmm.
So the system looks very, very good.
Sure.
But if I want to measure the pH value less than 4, how can I improve or modify the system?
Well, actually, we have done that and the stability in even 1 molar HCl is actually very good. And so it has a very high dynamic range to it.
Okay.
And
so what's the lower bound it can measure for pH?
We've measured down to pH 1 reasonably and up to 13, with it being able to give a linear curve, which we were kind of surprised at ourselves, but was able to be done.
You should put that into these slides.
Oh yeah, yeah. That was actually something recent that we had just gotten.
Any other questions? From UC Massachusetts? Okay, so if no question, today we end up a little bit earlier. Let's thank our 2 speakers one more time.